Hi, good evening all. This is Vishal Singhal from StealthStat, your host for today. Today we have Mr. Amar Singh, our deep learning researcher from StealthStat AI Lab. He'll be taking us through this topic of understanding different reinforcement learning methods to solve prediction and control problems. So I'll hand over the controls to Amar.
Yeah. Thanks, Vishal. Good
Go
evening,
ahead.
all. Yeah. I'll just share my screen.
Yeah, go ahead.
Yeah. So now we'll start with talking about reinforcement learning. Then we'll go ahead finding out what will be the best ways to find out prediction and control issues. Okay. So let us start. Agenda for this session you have. We'll first talk about reinforcement learning. We'll talk about principles. What are the various principles? What makes a reinforcement learning problem? Then we'll talk about the various concepts, terms which will be involved in the study of this concept of reinforcement learning. Then we'll talk about defining the optimal policy. That is, for a given reinforcement for a given problem, when we are solving the problem using reinforcement learning, what is the best solution? That best solution, we refer it as optimal policy. And last, to find this optimal policy, what are the different methods? So this would be the agenda for session now. So talking about, start with reinforcement learning. It is basically a decision support tool. It helps for decision making. And if we compare it with machine learning, you have got supervised, unsupervised learning. That means some data is there which is labeled, and based upon that you are able to work ahead predicting for the new input data. Or unsupervised, where you are trying to do clustering, or with the data you don't know what is the outcome, label is not known. But whereas reinforcement learning is also considered one way part of machine learning, but here the learning happens by trial and error process. Okay. Now you just consider a simple situation or a case of a robot trying to walk. So initially, how is the robot learning? That is, it is trying to do some trials, it is falling over, or sometimes it is walking up and able to make good steps. So this is the reinforcement learning is all by trial and error. There is nothing like a predefined thing. There is no such thing said to the robot that this is the action and this is good or this is not good. So this is about reinforcement learning. Reinforcement learning uses trial and error, and through that trial and error, it is able to come up with a good solution to a problem. It is generally used in situations where the data is dynamic. That means, whereas if you look at machine learning or deep learning, you have some image classification, you have some prediction to be made out of some data. Those things, the data is static there, and then you have to work upon finding out your whatever clustering classification. But by that, in case of reinforcement learning, it is like when by the time you are trying to work upon the data is very dynamically changing. So that is what is the situation which you will be encountering while you are trying to apply reinforcement learning. And it also involves numerous unrelated parameters. Like if you talk about a robot, or if you talk about anything, an aircraft moving around, so many things, it has to work upon gravity aspect, weight aspect, temperature, the atmosphere, so many aspects, so many unrelated parameters comes up. So reinforcement finds in applications like gaming, online, lot of gaming, robotics, and lot of complicated business processes. Reinforcement learning comes up. So where you have to automate the decision making process, that is where you can think of applying reinforcement learning. Yeah. Yeah. Let's talk about some of the terms before we look into what is reinforcement learning, let's talk about the terms. These are the common terms we will talk about, keep talking or referring about: environment, state, action, or agent, reward. So let me tell you about each of it, maybe one or two lines. Environment is basically everything which is relating to the problem. You can call it an environment. Like you think of a automated car. I mean the automated cars. These automated cars, everything surrounding the automated car, right? Across the front, back, or the sides, the road view, everything which is surrounding an automated car, and the car itself by itself also. That is all constitutes an environment. Or if you take a game of chess, the player, the rules of the game, the chess board, okay, all those things together make up the environment. Now, state is a subset of the environment. That means when you have to take a decision, when you have to take an action, you don't really need the entire environment. You will just need a small part of the environment which you are able to observe. And an automated car, when it has to move ahead, it is not able to see, or it doesn't need to consider the entire environment. It just have to consider the front part of it. Front, if there are no people around, nothing around, and it can move, take ahead. So that is what talks about the state. It is a small subset of the environment which is considered for the action. Right. Now, agent is the central part or the main part of a reinforcement learning. Now, agent takes actions, and agent is basically this algorithm, the reinforcement learning algorithm, which is trying to learn, and it is learning how best it can take actions, how best it can make decisions. Okay. Next, actions are something, a sequence of actions which helps the agent move from one state to another state. We'll keep talking about it more as we go about. Rewards, every action which agent takes, if the actions are good, it gets a reward. If the action is not so good, it may get a negative reward or some penalty, or sometimes it may not get a reward. So this is all about the basic terms which are involved: environment, state, action, agent action, and reward. Now this is the basic definition, or the basic how the reinforcement learning, the situation works out. Down you have the agent. Agent is the algorithm, reinforcement learning algorithm, which is taking an action. Okay. Now on the top you are all able to see S0, A0, S0, A0, R1, S1, A1, R2, S2, A2. So let me first explain you. Agent is there, A0, and the current state, the initial state is S0. That means across this, when it takes an action R1, it ends up in a new state S1, and new state again, once it ends up in a new state, again it will take another action A1, it will get a reward R2, then it ends up in the state 2. So here, if you go back to the picture, to the diagram here, agent takes an action. That means this action is influencing some environment or something, and as a result of the action, the agent is displaced to a new state. The agent is displaced to a new state, that is the state which is outcome of the environment, and also state agent receives a reward. So that means every action helps the agent receive a reward. Every action pushes or takes the agent to a new state. So here let us go back here. A0, that means A0. From A0, when it takes, A0 is the action. It will get a reward R1 and gets on to the new state. Next, it takes an action A1, gets a new reward R2, gets on to the new state. So this is a sequence of states, action, and rewards. This is what would follow. Yeah. Okay. So all this concept of states, action, rewards is all defined. It helps define the environment. Okay, so there is something called Markov decision process. That means you may not worry much about the name or the theory or as such. It is basically something which defines the environment. That means defining an environment. Let's go back slightly. Defining this environment. Okay, that means you should be able to know this environment constitutes which all states. That means it state S0, S1, S2, S3, that sequence of states that will define an environment. Okay, that means the sequence S is a finite set of states. That means various states within an environment. When the agent is taking an action, it will attain, go on to each of the states S1, S2, S3 onwards. And P is the state transition probability. Okay, I'll have to go ahead one more slide, then I think I'll be able to tell better. Now let's please don't look at the other aspect. If you look at a grid, the grid has got 1, 2, 3, 4, around 16, right? 16 boxes. Okay, 16 boxes. And if you observe, if you are in box 1, to go to box 2 or to go to box 5, there is some probability. Being in the box 1, I mean the box 1, there could be some probability of 0.6 going to 2, some probability of 0.4 going to 5. Okay, so from 1 to 2, 0.6, from 1 to 5, 0.4. So such kind of a probability, that means moving from one state, state 1 to state 2, state 1 to state 5, moving from one state to the other, the probability, that is, we refer it as state transition probability. That means state transition probability and states. This will together define the environment. What environment we are talking about here is made up of the states, and also we should be able to say what is the probability to move from one state to the other. Okay. Now when we are taking an action, that means action, this is action taken by the agent. Okay, so these actions are governed by three aspects. Okay, policy, value, or model. Okay, now let us look at this grid. If you are looking at grid 4x4 grid, it is these two shaded regions. One part near to one, you may take it as the initial point, and the final thing near to 14, you may take it as your goal. Okay, so from 0, this I'll call it as 0, and 14, this is the 15th one. Okay, so from 0 to 15, that means from the initial state to the final state to go, what is the specific path you may follow? You may follow a path called 1, 2, 6, 10, 11, and then you reach up. Okay, or you may follow path 1, 2, 9, 13, 14, and then you reach. So this policy is something which helps map from states to action. That means from one state to the other. It is simply giving a map. How do you reach from one place, one state to another state? That is what policy talks about. That means it is governing your action. Next. And now also here, if you are observing this, okay, you are observing this grid down right side. So this grid is a form of a policy. That means being in a particular state, what are the various places they can go? Okay, what are the various other states they can go? So this talks about the policy which governs the action. Another way of governing the action is values. That means if you go back to this grid down, each of the each of the state has got certain value. So it is basically aiming at increasing, maximizing the value. So if that is the case, so these values in these each state boxes, whatever states, this is something governing the action. That is the value. Okay. Model is something which is basically a rules of the environment. If you look at that is not presented here. Okay, model is like if you are playing a chess game, what are the various rules? Okay, if you are playing some other game, what are the basic rules of the environment? So these are the things: the policy, value, model. These are the three things which govern an action. Okay. Let's talk about the probabilities involved. Okay, there is something called state transition probability. There is something called environment probabilities. Okay, so let me just go back so that it helps you. I have talked about some probability here. Okay, here we have talked about some probability here in Markov decision process. That means this is the probability. Okay, that means from one state going back here from S0 to S1, from S1 to S2. So this transition, there is a probability involved. Okay, in this case, in this particular diagram, there may be a straightforward S1, S0 to S1, probability is 1, S1 to S2, probability may be 1. So this transition from state to state is called as state transition probability, which is referred by P. Okay. Then there is something called environment probability. Okay, environment probability is something which influences the action. Okay, so what is happening is the agent is, if you observe, is taking an alternate sequence of states and actions. State, action. Then there is a state and action. Then there is a state and action. That means there is a probability from state to state. That is P, state transition probability. There is another probability from action. When you take an action, there is an environmental probability which influences it to go to another state. Some instances, this is a very straight, clear example, but some instances when you take a particular action, it may end up, okay, when you are in state 1, you may take a particular action and you may end up in 5, or you may end up in 2, or you may take a particular action, you may. Okay, so these probability which is influencing an action is called as your environmental probability. So environmental probability will influence the action. State transition probability is influencing the movement from one state to the other. So basically these are the two probability which will be involved all across when it comes to the reinforcement learning problem solution. Okay, now we talk about the rewards. Now if you talk about this value, okay, these value here you are seeing in the left grid, you are able to see these values. These values in another term is, in a simplistic term, these are the values are nothing but the rewards. That means every action. Okay, before we talk more about it, let me tell you one thing. In reinforcement learning is characterized by the rewards which are not received at once. It is sometimes when they take an action, the rewards are immediate. Some instances the rewards are delayed across some time steps. That means a particular action when a player takes in a chess game, he may get an immediate reward or he may not get a reward, but the reward sometimes is spread across his other sequence steps. It may happen. So that means the reward, there is a delayed reward. Okay, that is characteristics about rewards in when it comes to the RL problem. So this rewards, now if you observe RT is equal to RT plus 1, RT plus 2, RT. That means now in this state, if you're going from state 1 to state 14, the sequence as you move on step into different states, you get some reward. Okay, R1, R2, R3. So RT plus 1, RT plus 2. So as per different states, you are getting some rewards. Okay. So this kind of a reward, agent's goal is to maximize the total cumulative reward. So as it is moving from one state to the other, it receive some rewards, and these are the rewards it has to maximize. Okay. Now, rewards generally are, as I told you, it is discounted. Okay, it is rewards are spread out across time steps. Sometimes you get the immediate reward, sometimes you get a reward later for the same step. So such a thing we apply a gamma. Gamma is a discount factor. That means when you move to another state, there is an immediate reward you get, and there is a possibility you will get the reward in the next step, but you are not sure. When you are not sure, you're discounted slightly, and after 2 more steps you may get some more reward, but again you are not sure at this point of time. You may further discount it with gamma square. So this is how you're discounting it to find out the current total reward. Okay, or the current total reward, or they also call it as returns. Okay, so this is how the reward calculation happens. Please note there is a gamma involved, which is the discount factor. That means when you are moving from one state to the other, there are rewards received, and some of the rewards are not immediate. So still we have to make some count of it. So we take a discount of the future rewards to calculate the total current reward. Okay, value function, state value function. Okay, now when this lighter circle, right, this is the state, and the darker circle are the actions. Lighter circles are the state, and the darker circles are actions. That means from a state, from a given state value function we are trying to calculate, from a state there is a chance you may take an action 1 A1, action A2. Okay, now here see here, value of a particular state. That means there is some probability, there is a sigma. Okay, sigma means this product of the probability and the action. Once you take an action, this is an action Q1, an action can be Q2, Q1 or Q2, and Q1 will have certain probability, Q2 will have certain probability, and then that is a summation. That is a total state value function. Okay, now here, action value function. In action value function, okay, when you take an action, you end up in one of these states, right? States are with this lighter circle, not darkened, lighter circle. So when you take an action, that means action values function means you are trying to look at it, initiate it from the action state. From action, when you go to a next state, you are going to receive a reward, plus you are also going to receive, okay, you are also able to make out what is the value you derive from the next state. Being in this state, what is the value? Being in this particular state, what is the value? And the state transition probability, as I have told you, state transition probability will apply. Okay, and this was the environment probability, okay, which applies for the action. This is the state transition probability. P is the state transition probability, which is applicable just before we calculate the value of a state. That means when you are taking an action, you receive a reward. When you're taking an action, you may end up in either this state or this state, or based upon that state, you have the state transition probability, product of the state value function. So you have an action value function. Given a state, from a state you take an action. You have a state value function. Given a state, you're able to take action. You've got action value function. From a state, you're able to reach at 2 states. So these are the 2 definitions. I am trying to avoid and trying to see less of max or less of equations are there, but still this is a minimal we need to be knowing. So that means the state value function helps us gets the action. So action probability, action value function helps us gets to the next state. So state probability, but specifically when you take an action, you have a reward. But when you're transitioning from state to action, there is no reward. Let's move further now. Okay, what is the optimal policy? Okay, now let me slightly go back. Now in this grid, if you take the shaded region near to 1, okay, near to 1, so that is the starting point, and the shaded region near to 14, that is the next part, between 14 and 11. So that is your goal. So reaching from this starting point to the goal, there are different methods, different pathways you've got. Okay, so those different pathways also you can refer it as policy. And here we are trying to find out this same policy, but optimal policy. And optimal policy is obtained by maximizing the rewards. Okay, so that means, and also each of the state has got certain rewards. That means some reward value, that is the value. Policy we talked about value. So that means each of the, if you are able to get maximum value by itself, it means it's a optimal policy. Okay, so you are following a particular policy 1, 5, 9, 13, 14, or you're following a particular policy 1, 2, 3, 7, 11, and then reaching there. So whichever policy which you are following, okay, and which it is, those particular states will give some rewards. So if you are able to maximize the reward, that is when you are able to, that is the policy, you can call it as optimal policy. Okay, now finding this optimal policy, this is the key objective of our this session. Okay, now some part of this session, I think it will overshoot. I may have one more session maybe, but I will try to sum it up as much as possible in this session. So finding this optimal policy, there are various methods. Okay, now before we find the optimal policy, I would have to like to talk to you about exploration and exploitation. Okay, now exploration is trying to generate new variables. You may just take it as a meaning of the English meaning of it. Exploitation is whatever known thing, whatever the known variables, you're trying to optimize, make the best use of it. Okay, so let me just go backwards again. That grid will help me to explain you better. Now, an agent is in state 5. The agent, as per policy, it has to follow 5, 6, 7, 11, and it is able to reach. Okay, so it has been told that is the policy it has been following in the past, and that seems to be giving good reward, and that is the same thing it is following. Okay, so that is the given pathway, the given set of states it is following. It is trying to exploit. That means whatever known thing, it's trying to work out more on that and work out the best out of it. Exploitation means it is now saying, okay, sorry, exploration is something it is trying to find out new paths. Okay, now it is trying to see, the agent now decides, okay, let me do some work, let me take 9, 13, 14, or let me take 6, 10, 14. Will I be able to get better rewards? So that means the known old things it wants to follow, the known proven things it wants to follow, that is exploitation. But it wants to experiment, it wants to try out new things, that is exploration. Now, a lot of examples. If you want to purchase something, you are going to a supermarket, there are a number of places where you can do your purchase, but the known place you would always like to go because you are comfortable, you always want to go, that is I can say it as exploitation. But if you say, okay, let me try out a new supermarket or a new place where I may get better things or better price, so that is exploration. So So it is simply to do with your English word and the meaning of it. So the agent is basically in the process of optimizing. It will either do exploration or it will do exploitation or exploration. One of these things it will do. So that is the optimizing the policy. That is to get the maximum rewards. I will once again check up this optimal policy. And optimal policy is obtained by maximizing the rewards. That means it has to just maximizing the rewards. It will follow the same proven old pathway. That will, it is going to exploit, optimize the known variables, or sometimes it wants to try out a new pathway. So this kind of a finding out optimal policy, and across these two ways, two methods or two approaches of exploration or exploitation, this can be done by three methods. Okay, methods to find this optimal policy. Now, do you have something called dynamic programming, Monte Carlo method, temporal difference method? Okay. Now, each of this method, when an agent is using it, it also depends on, you have to either explore, do the exploration or exploitation. Okay, so that to be done, still the agent has to work upon. So certain environmental factors also play prominently. Okay, those environmental factors which will help it to decide which of this, either to take dynamic programming or to take Monte Carlo method or to take temporal. It depends on the environmental factors. Okay, you remember we talked about the Markov decision process. That is the Markov process. States should be defined. State transition probability should be defined. Okay. So, and in fact, I'll add one more thing. There is state values. I mean, action values, or each value what you get, or each reward what you get for each state. So if you know the states, you know the state transition probability, and also if you know the rewards. So this defines the Markov property of a state. So if all these things are known, that is when you can apply dynamic programming. Okay. I would not, I'll take more time, maybe across another session, I'll talk more about it, and some coding will also be involved. But this session, I would be just summarizing and just telling you a quick part of this. So dynamic programming is used to find optimal policy when you know everything about the state. That means you know the state transition probability, you are also aware of the states, you're also aware of the rewards what you may get. Okay, whereas sometimes these things are not clear. Okay, when the rewards are not clear, or the states moving from one state to the other, if you look at it, let me tell you an example. You have a chess game, or the grid, action grid, what I was saying, 4x4 grid. The states are very clear. Okay, states are very clear. But when it comes to your some game, like you take a online any game, okay, Atari game or any game, you cannot say that the player is in state 1 and it has to go to state 2, or it has to go to state 3. There is nothing called a state. Okay, there's nothing called a state. So in that case, okay, state can't be clearly defined, whereas in a chess game or in a game of 4x4, state can be clearly defined. So in that case, dynamic programming applies, where the state you cannot define so clearly. Okay, and the probabilities are also more complicated. Okay, so that is when you are able to use your either Monte Carlo or temporal difference method. Further, Monte Carlo method you can use if the rewards are known clearly. Okay, or Monte Carlo method is known if you know the goal clearly. If, like for an example, in a chess game, you know what is the end. Okay, what is the end? Some problems you have an end point. But some problems, it is a continued state. In that case, you are not able to find out estimate of what is the total reward or the total end goal. So in that case, you can use temporal difference, but the entire starting point and the goal is known. In that case, you are able to apply Monte Carlo method. So these are the three methods what you can use for finding an optimal policy. And we will have one more session where I'll be explaining you detailedly. This is just this session we were trying to give an idea of what is reinforcement learning, the various variables, and let me take a quick summary of it. First, we talked about the application of reinforcement learning. Basically, it's for decision process. By trial and error, good trials, you make a good reward. Not a good trial, you don't make a reward. Then you have got, these are the governing things. These are the things involved in reinforcement learning: environment, state, action, agent, and reward. Then this is what the reinforcement learning, the entire any problem as such, if you put in the reinforcement learning, you have to put it in the form of an environment, agent takes an action, then it is pushed to a new state, and also it is getting a reward. So this is basically a reinforcement learning. Then we talk about what talks about a complete environment or a defined environment is the Markov process, right? It talks about the states, it talks very clearly about the probabilities. Then we talked about the policies. Policies is the pathway. Value is the numeric value or the numeric reward what you get. Model is the rules of the game, the rules of whatever the thing you're doing. Then we had talked about the two probabilities: state to state probability, moving from one state to the other. Then some probabilities which is influencing the actions. These are the two probabilities involved. Then we talked about the rewards, and the rewards which are discounted, because some rewards you do not get immediately, you will get over a period of time. Okay, so but still you need to make some calculation of it right now. So for that reason, we discount it. Then we talked about the value function. Being in a state, what is the value? Being in a taking a particular action, what is the value? In the case of action, you get a reward. But when you transition from state to an action, there is no such reward. Then we talked about optimal policy. Optimal policy is trying the best pathway. That means which is the various states you transition to reach your goal. And that is also true if you are able to maximize the reward, you are able to get to your optimal policy. Then getting an optimal policy, either you have to work out on the existing known variables or you have to try exploring new things. So these are the two ways, and these two ways can be done based upon with these three methods. But these methods which you choose depends on if you know about the environment fully defined, dynamic programming, and if you know the environment has got a clear goal, or sometimes when you don't know the environment clearly, some fact the states are not so clear, then you use either Monte Carlo or temporal difference. There are a lot of equations, lot of variables involved to this, which I will cover in the next session. So this is okay. Let me just tell you again. So when it is transition, everything states, our rewards and the probabilities are known. The state is defined. The environment is defined. You are using dynamic programming. When the environment is not clearly defined, okay, then you are using either Monte Carlo or temporal difference. And Monte Carlo still you are able to use when it is a limited sequence. That means you know the starting point, you know the goal, but in some instances you will not know the goal clearly. Okay, it is like some instances, some games or some problems, business problem, where it is a firefighting sort of thing, there is no end to it. So in that case you have temporal difference. That means temporal difference, nothing is known completely about the environment, and neither do you know about what is the end point of it, what is the end goal. So with this, I conclude. So we'll have one more session where I'll explain more about this three methods, and we'll involve some of the coding and more equations on these things. Thank you so much. Any questions? If you have, you can tell me.
So are you done, Amar?
Yeah, I'm done.
Uh,
There is not any coding now.
I believe you were to give a longer session today.
Yeah.
What happened?
1 minute.
So you will be giving it next time?
Yeah. No. Some part of it, this session I broke it. I will,
Okay.
some part of it I will continue in one more session. Still a
No,
lot to
so
it is there.
on another day or today?
On another day.
Okay. Sure. So audience,
Okay.
any questions so far? I'm not seeing any questions coming. So we have, so he has finished pretty fast. So yeah, something is coming.
Uh-huh.
Well, people are appreciating the introductory part of it. So
What part?
we will,
What part of it?
no. So people are appreciating your overall presentation. So audience,
Thank
we
you.
will inform you when he is ready with the next session. Today was supposed to be a 2-hour session, but I think he has broken it for next session to come.
Yeah, I thought a
Uh,
lot of content is there, so I wanted to be slow on this.
sure. So one question has come. So
Hmm.
state transition problem is affected by action problem.
Let me be slow. There is, okay. Is state transition probability affected by action transition probability? This is the question, I think. Okay.
Correct. Yeah.
Okay. No, these are two independent things. Once a particular, let's from state S1 to S2. Okay. Or let me go back to that particular part of the slide. Just a moment. Right. Yeah. Now we are in state 5. Okay. From 5 to 6 or 5 to 9, there is some probability. Being in 5, I may have a 0.4 probability of going to a state 6, 0.6 probability I may go to state 9. Okay. So this is the state transition probability. Okay. That means between moving from one state to the other, how is that happening? That is happening by an action, right? There is one probability involving when you go from one state to the other. Okay. Or let me first give you a complete summary answer. There is no, these two are independent. Okay. There is no such relationship between a state transition probability or an action transition probability. These together entirely are different. Okay. State is influencing the state moving from one state to the other. Environment probability is influencing the action. Okay. So now state transition probability, which is the P, the alphabet P which we are using, 5 to 6 and 5 to 9. So that is works out here between. But moving from one state to the other, there is some action involved. Okay. That means from the state you start, that means that action involved, that action. So that particular action is dependent on the environment. Okay. That means from a state, when a particular action is like, for example, a cricketer is there, when he hits the ball, okay, that means that particular action is dependent on the external environment. Or I am not getting any particular good example. So basically action and state
Value
probability.
function as well.
Anything
Yeah. So can you explain the value function?
value function? Okay, definitely. Yeah, state value function. Okay, so let's go slow here. This is, which is a lighter circle, is a state. That means from a state there is a possibility you may take two actions. Okay. So that means state value functions. That means being in this particular state, these are the possible actions you may take. That means this is the value of the state. Okay. Same way, taking this particular action which is a dark circle, this particular action, you may end up in these two states. So this is the action value function. Okay. So state value function, being in this state, there are possibilities of two actions. So that those two actions accumulate to tell us that this is a state value function. And taking this particular action, it may land us in this particular states. So this is accounts for your action value function. For state value functions, you are taking possible action. That actions are influenced by the action probability, environment probability. Okay. And when you take from the state, when you take an action, there is no reward. There is no reward. But when you take an action, there is an initial reward. Plus, based upon some probabilities, that means the state transition probability, you will end up in a particular state. So this is about your state value function and action value function.
Okay. Another is, do environment probabilities stay constant whatever state we may be in?
Environmental probability, okay. Okay, assuming that one instance it will assuming that it is expected to be constant, because when we study a particular problem, certain variables we assume it to be constant and work out upon it, right? So basically, state value function or the state transition probability or the environment transition probability, one instance if you take, they are constant. When they are assumed to be constant, we are working on dynamic programming. But in real life, in the real instances, both the probabilities vary. Sometimes the state itself, when you look at some particular games, the state itself are not clearly defined. Actions are also very dynamically changing, environment is changing. So both the probabilities may change. But assuming when we start solving a problem, we assume that they are stable, they are not changing. And when we assume such, and when we have such information and assumption that it is stable, then we use a standard dynamic programming. If it is varying, then we apply either of this Monte Carlo. Simple answer is it may vary. Yeah.
Okay. Any other questions, audience? So since we are not getting any more questions, we would like to close it here, and this session will continue over next one, and we will inform all of you in a few days.
Sure.
And people are appreciating, saying that it will help in foundation building, and very informative and good. Sure.
Yes.
Thank you.
We'll go with next
session. Thank you all, and
thank you so much.
Stay safe and sound, and thank you, Amar, for the session.
Thanks all. Thank you.